Hello, and welcome to our presentation on our project for COVID-19 Prevention Smart Lock. Next page.
This will be our outline for this presentation today. We've broken it up for the sake of clarity and brevity. We hope you'll enjoy it. We start out with the project backgrounds and requirements, which essentially is the what's and the whys. We will move on to the system description and equations and theories, which serve to explain how we're going to do what we set out to do. Now, next comes the design modules and descriptions. It's the nitty-gritty of the why we're doing what we're doing, everything that happens behind the scenes. Then we'll move on to the timeline from what we have proposed to what we plan on doing in the future. Then everyone's favorite part, the cost analysis, and then all that's left for us is to conclude and to answer any questions that may arise.
So here are the team members. I'd like to start off with myself. My name is Daniel Hong. I am the team leader, and I'm also the software lead for this project.
Hi, I'm Chris Coyle-Parampo. I am the hardware lead for this project.
I'm Adrian Diaz. I'm a computer engineer and I am part of the software team.
I'm Hasnat Malik and I'm the electrical engineer.
I'm Shahzeeb Siddiqui. I'm part of the hardware team and I'm an electrical engineer. So looking at our project, we know that during the time of COVID, safety is an utmost concern. So our idea is to create a lock that can be unlocked and locked with certain conditions using red pass and green pass. Next slide.
So we have a few different competitors from Yale to Schlage who use a variety of smart locks using all of the capabilities listed below, and we're going to delve into this in the next slide. So we can see over here that we chose NFC over everything else for a variety of reasons. Fingerprint and voice-assisted interactions present a unique difficulty as collecting data for them is quite difficult. Additionally, number pads are ineffective since we're trying to minimize human contact. And then finally, we can see we chose NFC over RFID and Bluetooth using our AHP table. And we can see that we wanted a very close range because we're trying to open a door. So we wanted to be able to open our door up close and personal. So that's why we were able to give the NFC the highest rating above RFID and Bluetooth. And then we can also see it got more points because it was a bidirectional communication type. And then finally, while it was the same setup time as RFID, it was much quicker than Bluetooth. And so based on these weighted scores, we were able to pick NFC as the best connection type for our project. And next slide.
So the reason why we chose this project is because it can definitely be helpful in the far near future. As mentioned before, we want to use red pass and green pass that usually is able to lock or unlock the door for the building. For instance, if someone has a green pass, they're allowed into the vicinity, whereas if someone has a red pass, it denies them entrance. Next slide. And as I mentioned, for the near future, when looking at it in a global aspect, it can definitely be extremely useful. It can definitely impact the globe. When looking at a medical view, the disease itself can only be suppressed and not stopped. And one way of suppressing it would be to minimize human contact, as Hasnat said in the slide before. Our lock can ensure safety, and since the human would only be using a cellular device, there would be no contact for anything. All he has to do is scan the cellular device against the NFC lock, and it would allow him access using the green pass, or deny him access using the red pass. Next slide. When looking at our system requirements, we need to look at a few things. The code for the NFC lock, which will be created by the software team, the person who has the cellular device that can lock or unlock the lock itself, limitations and restrictions of the lock, and the efficiency of the lock in the cellular application. Meaning we want the application to be extremely easy, it should be quick, and it's going to be combining multiple steps of verification in one single step. Next slide. Here's the needs identification. We divided into 3 separate categories. So one is that the device must be easily accessible by the individual that's trying to access the building or the or using the NFC reader. The second is for the lock, it must be coded in order to lock or unlock, access deny. And lastly, the system must be inexpensive and efficient. Next slide. And here's just the objective tree, speaking about the three aspects that we need: the easy accessible, coded, and the efficient. Next slide.
This is a broad overview on how we'll be implementing this smart lock. We'll be implementing a mobile application that will be programmed changeable NFC ID data. This data will then be read by our NFC module, which comes from in the form of a PN532 NFC chip. This chip encompasses the user interface for this lock. This chip passes the data onto the Raspberry Pi, which will check the tag against the data against a database, and depending on this interaction, it will either open the locking mechanism, or in our case, a servo-driven deadbolt lock, or it will notify you, the user, that you do not have permission to open the door.
Before even buying the materials and module for the design, we had to first make the calculations in order to ascertain the necessary requirements. Here we have the calculations for the necessary torque to turn the deadbolt lock. In the first equation, we have that torque is equal to the torque coefficient times the axial bolt force times the diameter of the deadbolt. The axial bolt force is in this equation below, to the side, determined through the equation axial bolt force, 0.7 times the tensile strength times the effective cross section of the cam bar. And this gives us 300, which is then implemented into the first formula, which gives us a required torque of roughly 1.08 Newton meters or 11.013 kilograms per second. We use this to decide on the high-tech HF 5645 MG. Next slide. The servo motor uses a different positioning system from the normal degrees or radians for angles. Instead, as seen in the input, it uses a pulse width. So this first must be calculated with the first equation seen above. Pulse width equals angles over 180 plus 1. And then we need to convert the angle into a duty cycle, which is how we use the positioning in the servo. And this is calculated with the formula below, angle over 18 plus 2.5. And we see this implemented into the code on the right, where we have the change duty cycle is 5. Next slide.
So we're going to move on to our behavior module. So as we can see, our input is going to be very simple. It's going to be a user scanning their green pass or phone to request access. And the output is going to be the deadbolt locking or remaining open. And we can see this through our data flow diagram on the following slide. So as we can see, these ovals are going to be our actors or users, and the italics are where the functions are occurring and the data is being processed. So as we can see, a human is going to arrive at the building. They're going to use their card at the NFC reader. This reader is now going to scan the card and read the data and pass it to our controller, the Raspberry Pi. And now what this Raspberry Pi will do is it will compare the information and request access from the database. And now this database, if the green pass is there and permission is granted, then it will send a signal to rotate to the servo motor. And now this servo motor will turn the lock pin to the open position. However, if access is denied or there is a red pass, this will be an invalid info occurrence and there will be no change occurring to the lock and the deadbolt will remain closed. And the human will be requested to try again. Next slide.
So here's a table and a figure for the level 0 functional decomposition. It shows the smart lock system as a whole, where the two inputs are the RFID tag and the 5 volts DC power with a 3 amp current going into it. We are using the RFID tag for now until we have a application up and running for the NFC input. And it will output a voltage signal with a specific pulse width to the servo so that it could rotate to see if the door is unlocked or locked, depending on if the correct tag is red. Next slide. Here we have a more detailed level 1 functional decomposition, which shows the 3 modules within the system. On the top left, we have the NFC/RFID module, which can do both inputs and outputs for NFC and just inputs for RFID. It uses the P532 chipset, and again, we are using the RFID tag for now as the input. It also takes a 5 volt DC power from the Raspberry Pi. On the top right, we have the servo, and it also takes a 5 volt DC power from the Raspberry Pi, and it also takes a voltage signal carrying the varying pulse width in order to determine which position it should sit in, whether that be unlocked or locked. Next slide. Here's the information I just stated about the two modules. Finally, we have the Raspberry Pi 4 to act as interface between the two modules. And later, when we integrate a database, it will have another input for the Raspberry Pi. Next slide. Oh, here we have the software design. It is shown in a flowchart like this for ease of understanding. However, the information was said before in the data flow diagram, so I don't want to repeat it. So next slide. Here is an example of the software. As you can see, there are 2 values for Boolean and 2 values for string, each of them coming right after the other. One was from the red pass, one was from the green pass being true, the red pass being false, and they both have their ID values written on top of them. Next slide.
Okay, this is a breadboard view of our project. As we see, there are 4 main components as of right now: the Raspberry Pi, which are the brains of the project, the NFC module, the server, which will be connected physically to the Deadbolt, and the power supply, which was implemented to provide a supplemental power.
Here we have the servo test, which will be sweeping the servo. It's a simple code just to test the performance of the servo. And in the video, we see that the servo's arm is sweeping back and forth. And during this testing phase, we were just trying to see if there were any errors, and we did encounter some errors, which were later solved through voltage correction. Next slide. Here we have the NFC test. And in the NFC test, we're simply testing the NFC module when wired with the Raspberry Pi. The goal of this test is to see the functionality of the NFC module when using the conditional statement as Dan stated before. And what this statement does is we first pull the UIDs from the tags, and then it outputs the UIDs and the Boolean output corresponding with those UIDs.
This here is a physical picture of the circuit we made in the graphic that we showed a few slides ago. Now, you might be pointing out at this point, guys, there used to be a black power supply in the graphic. Where did that go in this picture? We'll be giving an explanation to that in a few slides, but the short answer could be said with the word iterations. Now, as we see here, this is one of our first integration tests where we put all of our separate modules together. As we see, when we put the blue tag near the reader, nothing happens in the system. The blue tag reads as false in the Raspberry Pi. However, when we put the white card by the reader, the servo starts moving. The white card is treated as true in the Raspberry Pi. In terms of passes, the blue card could be considered to be a red pass, and the white card can be considered to be a green pass.
So we went through a few iterations while in the process of creating this project. The first one on the software side, when trying to use the NFC module with the Raspberry Pi, we failed to use the SPI connection method. This was due to the lack of a library and database in the online. When trying to look for it, the web page was missing. So instead, we used the I2C connectivity in the current iteration, and it poses no difference for us. Like Chris said before, there used to be a power supply, which we added in order to avoid current draw problems, but due to voltage difference issues, we had to remove it. Next slide.
Now, in this video, we see that we've added things from the previous implementation. We used Protodo to mount the servo to the wood board so that the servo will have a strong foundation to manipulate the lock cam bar. This video is our 40% mark. We've added an LED to serve as a visual indicator that the blue tag fails at opening the servo lock. We can see this happen, and then we can continue to watch how the white card, which serves as our makeshift green pass, operates the lock. If the video plays. Hopefully. There you go. The blue pass comes, the light turns on saying that you have no access, and now the white card will come acting as our green pass, turns off the light and opens the lock or activates the lock.
And over here we can see our proposed timeline, and unfortunately due to complications this fell apart closer to the end. However, we were able to build in extra time, and using this cushion of time we were able to complete our project on time as shown through our milestone in the next slide. So as we can see through our 40% milestone, what we achieved was the building of our Deadbolt and NFC reader connection. And essentially what we were able to achieve, and which is what we were trying to achieve, was that the Deadbolt opens and closes according to the signals from our Raspberry Pi NFC interface. And going on to our next slide, we can see that for our next semester, we will be spending winter break using it for some extra learning and also being able to refine all of our parts up till now. And next slide.
Here we have the cost analysis, and we have the most expensive thing on our project is the servo motor. And we have some supplementary materials such as the construction materials and the lock, which were provided. And the total cost of all the materials came out to $124.71. Here we have the conclusion of future works. As seen, we completed the 40% milestone, and throughout the winter intersession, we will be working on the implementation of an SQL database, and we will be integrating this within the project, hopefully in the second half of the spring semester. The hardware team will also be keeping an open mind towards other possible lock designs for optimization during this time. And for the lessons learned throughout this project, we realized the importance of time management and how it's necessary to keep an open mind to discover new solutions and possibilities to problems.
So here are some code standards and constraints that we're using. We are using 3 standards. The first one is the ISO 14443. It is a standard for RFID and NFC interfaces, mainly for RFID tags used in proximity systems, and is generally aimed for use in payment systems, which is good for us because we want to create something similar to a mobile card or ID. The second one listed is the ISO/IEC 18092/ECMA 340, which is based off of the previously mentioned ISO 14443, but is specifically for near-field communication, its interface, and its protocol. The standard will tell us about its coding, transfer speeds, and initialization schemes for both passive and active NFC modes. Finally, we have the IEEE 802.11 standard, which is used for Wi-Fi, which we plan to use if we do not want to use Ethernet in the spring semester.
Through the design process of our project, we were focused on the safety and security of our users. The project, as an implementation itself, was to help institutions keep their staff and clients safe by providing them with a contactless option for verification purposes. In the testing phase, we realized it could be possible for a user to accidentally scan their credit card or something equally confidential. We made sure that our software doesn't save any of the scan data for any longer than it takes to check the database if it's a valid pass. In our wireless implementation, we use the IEEE standards for wireless communication, so we're not transmitting any data in an insecure fashion. One consideration we're still trying to resolve is the misuse of our project. Theoretically, our project could be modified and implemented to cause discrimination against the population, even when that was never the original implementation. We will be working to find solutions to this dilemma over the coming months. These are the references that we've used to compile this presentation. Thank you. Are there any questions that you have for us?
Thanks, Joyce, for the informative presentation. Good work. So do we have any questions from the audience? Okay, if not,